So welcome back, and we're on to our next lecture topic of the General Chemistry Review. And this one you might not be very fond of if you've heard it before, and I hope that you have. And it's called Electron Configuration. Okay, so Electron Configuration, what is it? Why do we use it? Why did we make it go through this mess? Well, think of Electron Configuration as a Google map. It is a Google map where every electron is located. It's going to give you the locations of those electrons. Now, when I say that, we can't really get exact locations of an electron. We can give you a roundabout idea. We can tell you what road they're on, but we can never really tell you where that house is going to be located on that road. And that's the purpose of electron configuration. All of these total electrons, all right, the total electrons, and we already know how to calculate that number. There's no actually calculation at all. We look at a value, right, that atomic number. If carbon has 6 total electrons, then we can apply a map to all of those 6 electrons. And we can tell you where they are and where they're going to be located in the general vicinity of things. Okay, so before we start into this mess, something that I need to tell you about, and that is the football field. Remember I told you that these electrons can just run around in the football field wherever they want to go. All right, well, that was a kind of a good analogy at the time, but quite honestly, they are restricted. They can't really just go wherever they want to go. Okay? They're there. They're in the football field. They're playing around with all the other kids, so there's other electrons that are present. But they really do have rules and regulations in place. They can't just go wherever they want to go. One of those rules and regulations is something that we call a subshell. Okay? So what you are going to figure out with me is that I like to look at electron configuration maybe in a different way than some of your other instructors. Number one, all of the electrons have what we call a major orbit that they will play in. All right, so this is the main highway. And off of this main highway, we will have something called a subshell. And that is the road or the exit that we're going to take off of that main highway that we are going to find these electrons in. These subshells sometimes are called atomic orbits or orbitals, but if we're using the term major orbit, I think major orbit and atomic orbits will get you confused if we're not careful. Out of these subshells or atomic orbits, we will see different types of roads. You know, sometimes it will be a 4-lane. Sometimes it will be a 2-lane. Sometimes it will be a gravel road. Sometimes it will be a dirt road. There's different types of subshells that are out there for these electrons to be found in. And those are going to be called S, P, D, and F. That is how we designate the subshells that we will find these electrons. Now, we really only pay attention to valence electrons. That is what drives the chemistry of organic. But the electron configuration will give you the map of every electron that the atom has. As far as the shapes go, subshells have shapes. Again, they're different. I gave you the analogy of the road. Different types of road. There's different types of subshells. For the S, I want you to think S stands for spherical. So that means that here we have a nucleus of an atom, and around that nucleus there is a spherical path that these electrons can take. If they are in that path, they are designated as the S subshell. Now, that S subshell can get bigger and bigger and bigger, depending on the atom. So it could be a sphere that's really close to the nucleus, or it could be a larger sphere that is a little further away from the nucleus, or even a bigger sphere that goes even further away from the nucleus. But that is the general shape of S, a sphere. Okay, what about P? Well, P's are what I would call a figure 8 or a dumbbell. So we get a lobe that comes to the top, and we get a lobe that comes down to the bottom. There's your figure 8 shape. Here in the center, this area, there's a rare chance of finding electron, almost zero. And this is called a node because it's no man's land. Node, right? Nothing's really going to be there. It's either in the top lobe or it's in the bottom lobe. So again, if this is the nucleus, if it's in a P subshell, this pathway is going to either be up or down. It can get bigger, right, and more exaggerated, or it can get even bigger depending on the atom and even more exaggerated, but that is the shape of what we would call the P subshell. All right, now let's take a look at D. D is going to be a 4-leaf clover. It's going to be like the P, but we're going to have one to the left and we're going to have one to the right. And there's still a node that's on the inside of that as well. And then F adds another layer. So you get this 4-leaf clover shape, and then you're going to add 2 more nodes onto that, one pointed forward and one pointed backward. And for F, I'm actually never going to ask you to draw that on a test because for some people, a lot of people, it's very difficult to do so. You got to show it in 3 dimensions. So computerized models are great, but on a sheet of paper, it sometimes is a little bit more difficult for people to draw that the proper way. So the shape of the S is spherical, the shape of the P is a figure 8, and the shape of the D is a 4-leaf clover. So this is the path that the electrons can take if they are designated in one of those spots. Now, let's kind of get to it. Now that we have a general background of this thing, we have hydrogen on the periodic table, right? So if I pull up the periodic table, here we go. Here's hydrogen. We're going to start there. There's a first. And what we're missing off of this periodic table are the period numbers. Well, the period numbers are over here to the left. Period 1, period 2, period 3, period 4, period 5, period 6, and period 7. What about these 2 down below? Well, if you notice, there's a blank spot here and a blank spot there. That is where these actually get inserted. So the periodic table actually needs to extend. It needs to elongate left to right-hand side because we need to actually squeeze those bottom rows into that spot and stretch this periodic table out. But because it would squish all of those elements and information together, we just take that out and we put it at the bottom so that way we've got something that looks a little bit better as far as representation goes. Well, hydrogen, we need the electron configuration for. And here's the deal. Anything that's in these 2 rows or columns, these 2 columns, those are all regarded as the S subshell. If we stop or if we go through elements in this area, we are going through S's. Okay, well, the next one we talked about were P's, right? So the P's are actually going to be located over here to the right-hand side. All of those are your P blocks, folks, right here. Again, the table is structured a certain way, and this is one of the reasons that it has this shape. I told you it was a very organized piece of literature, and now you're starting to see that even more so. So all of the P subshells will be on the right-hand side after you go through the valley. And if we go through that area, or if we stop in that area, those electrons will be on the P subshell. The transitions, all of those with the B's, right? All of these. These transitions are where they are located, and we see the valley and the shape. One of the reasons that we see the shape the way that it is because all of those are a different subshell. And that subshell will be D. And then you guessed it, the two at the very bottom, down here. These two rows are pulled apart, not only to make the shape of the periodic table a little bit better, but they are pulled away from the table and slapped down at the bottom because these represent our F's. Folks, this is another reason this table is shaped the way that it is. It's giving you insight of where these electrons are going to be located as far as electron configuration goes. Hence, why this isn't a nice, complete box that you would have questioned earlier or in a previous class. So SP, Ds, and Fs, that's where they are. We need to draw the electron configuration of hydrogen. So how do we do it? Well, we start off with the row. It's in row number 1. So hydrogen gets 1. We also start off over here to the left in the S block. So we write down S. And hydrogen is the first one. And we didn't have to go any further. And because of that, we write a superscript, first one out of the block. So hydrogen's electron configuration is 1s1. Okay, well, what about helium? Let's go to the next one. Well, helium's going to be kind of weird. All right, so I told you that everything to the right-hand side is going to be P, except for helium. In this case, helium really actually needs to be in this spot right there, which is one of the reasons that that shape is there like that, okay? But helium has characteristics that are like neon and argon and krypton and xenon and radon. So because of that, he really does fit into that very last column over on the right-hand side. But with electron configuration, he really fits over here near hydrogen. I didn't say this thing was perfect. I said that it was a very good organized piece of literature, but nothing's ever perfect. And this is one of those cases. Helium actually needs to be over here to the left-hand side near hydrogen where that empty space looks like it would fit. So if I do the electron configuration for helium, I start off again in row number 1. All right, so 1. I also start off in the S subblock. Okay, so I write down S. We said that helium really deserves to be over here to the left-hand side. It's really one of the only exceptions with this. And to get to helium, I go to hydrogen, 1. Helium is second. So this is a 1s2. We're going to work on. We're going to now go to lithium, which is number 3. Now, electron configuration includes everything. All electrons, not just the valence, but all electrons. So I always have to start up here to the very top of the table. So I start off in row number 1. I write down 1. I start off in S block. So I write down the S. And I do hydrogen 1, helium's number 2. So 1s2. Then I go down to the next row. When I do that, I'm now in row number 2. So I write a big 2. Lithium is in the S block. It's to the left. So I write down S. And lithium is the very first one in that block. So 2s1. There is your electron configuration for lithium. All right, now let's do it with carbon. I'm going to skip a few. But we start up at the top, like always. I start off in row 1. There we go. I start off in the S block. So I write down S. Then I go hydrogen, and then I go helium. So 1s2. Then go to the second row, where carbon is going to be. I start off on the second row, so I write down a big 2. I start off in the S block, because I have to. I have to go through those in order to get to carbon, so there's S. And lithium and beryllium, so S1, and there's S2, so 2s2. Now the issue is that I have to jump. I go from the S block, and then I go over here to the right-hand side where the P block is at. So they really would like for you to write the row number again and symbolize that you are now in the P section, not the S section. And then I go to carbon. Carbon's 2 over. So this is boron, P1, and carbon is your second one, so that's a P2. And there you go. There's the electron configuration for carbon. 1s2, 2s2, 2p2. I'm going to work down a little bit further. We're going to do magnesium now. Magnesium is going to be number 12. So I start up here at the very top again in row 1 in the S block, and hydrogen and helium are there. So magnesium, 1s2. Then go to the second row, 2s2. I then go to the third block, or to the second row again, over here to the P block. That's still a 2, P. So I'll write that in. 1, 2, 3, 4, 5, 6. You have to go all the way across. So 2p6. So I then go down to the third block, because that's where magnesium is going to be. So I'm going to write down the big number 3. I'm also going to start off on the left-hand side, and that is the S block. So I'm going to write down S. And then to get to magnesium, I count 1, 2 over. So this is 3s2. So the electron configuration for magnesium, 1s2, 2s2, 2p6, and 3s2. All right, if I keep trucking on, I'm now going to do something in the transition. Something in the transition valley, and let's do maybe copper, number 29. So I start up all the way to the very top again. So this time I'm not really going to leave the periodic chart. I'm just going to write it down here at the very bottom. That way I don't flip on you all the time, right? Okay, so, or maybe here at the top. Let me erase this. So copper, if you notice, of course, is in a different color. That means it's in a different block that we haven't used yet, and that's going to be in the D block. So how do we treat the D block? Well, we treat it no different than some of the others, okay? There's just one slight exception. So if I want the electron configuration of copper, up here at the top, 1, I start off in the S block, and that's hydrogen and helium, so 1s2. Then go down to the next one. The next row is a big 2. I start off in the S block. That's lithium and beryllium, so there's 2 of them there. I then skip to the green. Well, I need to write down the big 2 again. I need to tell you that I'm in the P block now. And I have to go through all of those in order to get down to the next row. So 1, 2, 3, 4, 5, 6, 2p6. I then go to the third row, so I write down the big 3. I start off in the S block, so I write down S. And I go through sodium and magnesium, which is 2 of them. I then skip to the green area again. That's now my P block. So just like before, I write down the 3 just to confirm that I'm still in the third row. I then write down the P block to let you know I'm now working in a different subshell. And I count all the way across because I need to go down to the next row. So 1, 2, 3, 4, 5, 6. There's 6 of those. There we go. The next one, I'm in the 4th row. So I write down a 4. I'm in the S block, that's where I start with, so I write down S, and that's potassium and calcium. So there's 2 of them. I then go into the blue area. This blue area represents the Ds, all right? So you would write down 4, and then there's a D area here, and then I would count over until I get to copper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 49. And then you would turn that in and say, here's the electron configuration for copper. I've used the rules that you've just given me. And the answer is you would be wrong. That's not the electron configuration for copper. Why? Because the Ds fall 1 behind. What do I mean by that? Well, instead of the 4 here, it's actually going to be a 3. This is in the 4th row, but D's fall 1 behind. So instead of 4D, this would be 3D9. In the next one, this is row 5. But these D's would actually be 4D. This 6, row 6, but this is 5D. Row 7, but this is actually 6D. They always fall 1 behind of the row number, the period number. Why? We'll talk about that in a later video. The F's that's down here below will eventually do one of those too. Those F's will fall 2 behind. So keep in mind that this row is 6 and this row is 7 because they need to be squeezed into those areas. So this is actually going to be a 4F area, not a 6F area. And this is going to be a 5F area, not a 7. Again, we'll address that in a different video. So just when you think the getting was good, just when you think that you were getting this electron configuration and you were like, this is pretty smooth, I now throw in a monkey wrench, and that wrench is going to change the number in front of D's and in front of F's, and that's something that you've got to remember when you do electron configuration. And the reason we will talk about, it's not just something that's made up to make your life miserable, but there is a reason for it. So in the next video, we'll continue on with electron configuration, and we'll do more complex examples, and we'll bring in more of the D's and we'll bring in more of the F's, just so that you can feel a little bit more comfortable with those.